Hello everyone. Today we will be talking about issues related to motion perception and also color for our psychology or for our sensation and perception course this week. So let's begin by asking ourselves this important question. Why is motion perception so important for us? Part of the aspect that motion perception is so important for us is really that it's a survival mechanism. So part of what we want to be able to do is if we want to accurately be able to survive in the environment, we need to be able to detect if there's a predator out there in our environment that we should be able to capture our attention if something changes within our environment. So if we don't expect that there should be any motion that occurs within our current situation and we do observe any type of motion, our attention is going to be directly called to that specific spot so that way we can try to attenuate and try to perceive and also try to recognize to a greater extent what that object might potentially be, either a threat or not. So it's very important for us to being able to perceive these objects and also events within our environment. And we have to understand that in some instances, objects can definitely move within our environment, or potentially we may move also within our environment. So it's important for us to be able to understand that objects are not always going to be stationary, but rather they may be traveling through time and space. So there's a lot of different factors that we may need to consider in terms of object perception, not just is the object there or not, but rather what's the distance of the object to us? Is it a threat or not a threat? How fast is the object moving? And all those different dimensions. So part of the issues regarding motion is that sometimes our motion perception is not always accurate, and sometimes we have failures in terms of disabilities or factors that are abnormal in their nature that might potentially contribute to issues related to us failing to recognize objects correctly, such as what we call motion agnosia. With motion agnosia, we find that there's damage to the cortex that results in an inability for an individual to perceive movement. And unfortunately for the person, they essentially are skipping steps, just like our images show here. At one point, the cup is filling. At the next point, the cup is much more filled. At the next point, the cup is already overflowing because the person has an inability to identify or distinguish all the different sequences that are occurring within the filling of the cup. But rather, it goes in a very extreme fashion to the point where we may have failure to be able to recognize that there was a sequence of movement of that specific liquid in this particular case. So as you can imagine, this is a very debilitating type of disorder. Now, additionally, part of what we may want to concern ourselves with is we may want to concern ourselves with the issues of how we can change the object's location over time. Now, part of what we actually see is regarding our motion after effect. And with our motion after effect phenomenon or illusion, this is where we have the illusion of motion of a stationary object. So just as our image is showing you here on our screen, our object is not actually moving in any capacity, but yet our brain gives you the indication that it is moving. Why does this actually occur? The motion after effect actually occurs because we have prolonged exposure for about 15 seconds or more to potentially a moving object, and now all of a sudden we have a response from our neurons that assume that we should potentially see an object that should be moving. Within this week's course content, there should be a link there provided for you that demonstrates the motion after effect a little bit more specifically and shows you how it is that our objects can potentially move within those different types of situations. So even though the object is stationary, we give you the illusion of movement, and now all of a sudden when we stop the movement, it still provides you that illusion of movement in those particular cases. And why does that happen? Because our neurons have become suggested that they should be looking out for movement, or that movement should exist, but in reality movement does not exist, but yet the illusion remains and the neurons still respond as if movement were to potentially exist. So when we look at this issue associated with our neurons, we need to have specific neurons or detectors that respond to specific motion. Again, there's also a link within Blackboard this week that will show you a little bit more specifically as to how specific neurons may respond to different forms of movement. So I definitely recommend that you look at that specific link and you can try out that demonstration in a couple of different ways. And the idea associated with this computational view of motion detection with these specific neurons is that we have to have these specific detectors that would respond to right to left motion versus left to right motion. So it wouldn't do us any good to have just one specific detector that responds to any type of motion, because it might potentially get confused as to what type of motion might be existing. Is it right to left or left to right? But rather, we would have specific types of neurons that potentially respond to different movement across that visual field of that neuron or of that specific detector that we would have. So the stimulus would need to cross through that specific receptive field, and the crossing of that receptive field would indicate for us if that specific neuron turns on, and if it does, it would send the signal that it's left to right or right to left motion. So the idea here is that sometimes objects aren't necessarily moving. So if you think of, for instance, the idea of what we call apparent motion, and with apparent motion here, we're talking about something like a movie. So here with movies, they give you the illusion that the object is actually moving, that the person's mouth is actually moving, when in reality there is no real movement, but rather it's a very fast sequence of images that are being presented that gives you the illusion of movement. So here, think of a flip book. If you've ever had like a cartoon flip book, or cartoons themselves, or even movies, or anything that is a video. It's actually just a bunch of images that have been taken very, very fast and then played at a very fast speed to create that illusion of movement. So here, with this potential problem of apparent movement, we also have the issue of what we call the aperture problem. And the aperture problem is the following: that we may have initial movement initial movement detection that is okay. But if, for instance, we place a mask or repeat the same movement, this creates a different movement pattern for us and ultimately demonstrates the competition between different types of detectors that we would have. So going back to the issue here of what we were just talking about in our previous slide, of having specific neurons that respond, we may actually create different responses from different neurons, even though that response may not be looked for, depending on what kind of stimulation it is that we give those specific neurons, thus potentially providing for us an illusion that we might have in terms of giving the wrong information or the wrong response. Now, what are three situations that lead to motion perception? Number one, the object moves and the observer is stationary. If that were to occur, the movement that creates an image that moves on the observer's retina in that particular case, versus an object moving and the observer following the object with his or her eyes, and that creates the movement that tracks that the image can actually be stationary on the retina rather than changing its different locations. And third, an observer moves through a stationary environment, and this ultimately creates an image of the environment that moves across the retina, but the environment is perceived as being stationary. So perception does not necessarily depend on only an image on the retina, but it also depends on how it is that we track the objects. Are we moving? Are our eyes moving? Is the situation in the back moving? The environment? What is it that's changing within that environment that ultimately can lead to motion perception? So here, for instance, we have the three scenarios. With scenario A, Jeremy walks past Maria and Maria's eyes are stationary, and it creates that motion perception because that object is moving through time and space. With B, Jeremy walks past Maria, but Maria follows him with her eyes. So here, as she's tracking him, the background is also changing, thus giving the perception of movement. And last, Maria walks through the scene, and as she's walking through the scene, she is moving through it. And again, there's different aspects of the environment that are changing, thus giving the motion aspect associated with her perception. So when we look at motion perception, our brain is a very important mechanism that's ultimately going to be able to help with the detection of motion, because again, our neurons are sending that signal to specific brain areas. But what brain areas are very important for motion detection? For motion detection to occur, area MT, or what we call our middle temporal lobe, is actually believed to be a very important factor or a very important region for motion perception. Now, the way that we actually have been able to identify this is that if we actually create lesions in this region, this actually impairs the ability to detect direction of motion. And 90% of the neurons that we actually have within area MT are actually sensitive to directionality in those specific instances. So again, giving us a very good clue as to where potentially localization of functioning may exist within the brain that might indicate for us motion perception. So in summary, what does it all mean in terms of motion? Motion perception is really an automatic process. This isn't something that we can tell our brain to do or not do. And that's why illusions occur in terms of movement, such as the one that we have on our left and also the one that we have on our right. So activation of the detectors within our eyes are going to be very important for the aspect of perception of movement. But in our brain, we have to have the interpretation. But yet it's not always accurate that we will actually have an interpretation of movement, because in some situations, the object may not be potentially moving, but yet we've already established for our neurons to give the illusion that movement is occurring, thus providing the illusion of actual movement. All right, so let's move into talking about our final topic of conversation for this week, and that topic is color vision. Now, when we're looking at color vision, what are some of the basic functions associated with color vision? Number one, color signals actually help us identify and classify specific objects into what their specific categories are supposed to be. Number two, color facilitates perceptual organization of elements into the specific objects. And number three, color vision may provide an evolutionary advantage if we were looking at it from that perspective in terms of foraging for food. So if, for instance, we were to go out into our environment and we've had the experience of actually seeing the fruits and vegetables on our left versus now seeing the fruits and vegetables on our right, this might potentially be an evolutionary mechanism that we use color to indicate what is it that we assume to be something healthy, or what is it that we assume to be something good that we can actually eat. So if you've had the experience of having orange carrots, yellow bananas, green spinach, or green lettuce, and now all of a sudden those colors change, that may be indicative to you that potentially this isn't something that's going to be good for you, that it may potentially be hurting you in those particular cases. So here it's important for us to understand also how color can actually indicate for us differences in terms of emotions, differences in terms of being able to classify specific objects as well, and using that aspect of color into specific features for what it is that we can actually see. Now, in terms of color and color vision, the actual spectrum that we have available for us to being able to observe, that we measure in terms of wavelengths, is between 400 to 700 nanometers. This is a very small range of the visual spectrum that we can actually be able to potentially perceive, especially when we think that there's other types of wavelengths that exist outside of what it is that we can actually perceive. So we can only perceive between 400 to 700 nanometers, but things exist below the 400 nanometer range and also above the 700 nanometer range, such as X-rays, gamma rays, ultraviolet rays. We also have infrared rays, we have FM waves, TV waves, AM waves, and so on and so forth. Those are things that we cannot perceive in terms of their visual spectrum, but yet they exist out there in the world. So we are very limited in terms of what we can see, which again gives us this idea that yet we are very sophisticated as a species, but yet we are still quite limited in terms of what our capabilities are using the specific senses that we have available to us. So if we look here at the issue of color vision, there's a very important theory that we need to talk about, and that is the trichromacy theory. The trichromacy theory essentially explains the following: that we have three different types of receptors that ultimately can be used in terms of perception of wavelengths. Now, before we get into those, we need to talk a little bit about the retina, because the retina is very important, because the retina contains two very important elements, the rods and cones. Rods are very useful for when we have sensitivity to low levels of light. Now, this is what we call scoptic vision, where light intensities that are bright enough to stimulate the rod receptors but are too dim to actually stimulate the cone receptors. So here we do have some level of light that's coming in, but it's not something that's going to be strong enough for us to being able to activate our cones. Think of it as night time vision. So in other words, you're in your room at night, you've turned off all the lights, it's very dark, you can see rough objects after a specific given time, but you really can't extract any type of details. And the reason for that is because rods are not sensitive enough to being able to grasp the details. And here, rods themselves don't actually have any aspect associated with color. That's why we see things as being black and white at night, unless we have a specific light stimulus that has a specific color. So if it has a color of green or red or whatever the case may be of whatever your clock may be or whatever the night light is, everything has now that perceptual tone of that specific color because it's being reflected and absorbed by what it is that's being given off by that specific light source. So here, think of this aspect of rods again as being very sensitive to low levels of light, but they're not going to be able to extract a lot of details. Versus cones, where cones now are very sensitive to higher daytime levels of light. We call this photopic vision. And photopic vision is essentially where light is bright enough for us to be able to stimulate our cone receptors. Now, the reason that this is so important for us is that cone receptors are the ones that are very important for color vision and extracting of details. Now, here when you think about the fovea, for instance, that exists on our retina, our fovea is the the area where we really focus in on that image and we're able to extract a lot of details and a lot of information. And the reason that that happens is because they are very sensitive to those higher daytime levels of light, and they are filled with cones. The fovea is filled with cones, and it's able to extract and have the maximum response from the cones with that level of light that allows us to be able to extract details associated with that stimulus, and that includes the issues related to color. Now, within our trichromacy theory, the trichromacy theory proposes that we have three different varieties of cones. We have what are called our S cones, our M cones, and our L cones. Each one of them is sensitive enough to a specific type of wavelength. So for instance, our S cones are what we call our short wavelength cones. These are the ones that peak around 440 nanometers. Okay, so here, if we look on our graph, this would be our green line that we have here. Our M cones are the cones that are sensitive enough to middle wavelengths, and these peak around 535 nanometers. So again, here now, this is what we would look at, that is our purple line. And then last, we have our long cones, and these cones are the ones that are sensitive enough to wavelengths, and those peak around 565 nanometers. So here, this would be our orange line. Now, according to trichromacy theory, the idea of color perception is based on the response of all three different types of cones, not just one single wavelength or one single type of cone, but rather all three of them combined together to create the illusion of whatever that color may be, or the perception of what that color may be. So the responses are varying depending on the wavelengths that are available to us, and the combination of the responses across all three cone types lead to the perception of all colors. So color matching experiments actually show that colors that are perceptually similar, right, what we call metamers, can be caused by different physical wavelengths in those particular cases. Now, one receptor type cannot lead to color vision for the following reason. Absorption of a photon causes the same effect no matter what the wavelength is, but any two wavelengths can cause the same response by changing the intensity of it. So two receptor types, what we call dichromats, solve this problem by having three types, what we call trichromats, so the idea of trichromacy theory that actually allows for the perception of more colors to exist. And that's why we propose trichromacy theory, because using all three different wavelengths and three different types of cones are going to be enough to being able to provide you all the visual spectrum of the colors that are available to us. Now, this is important because we do have color deficiency that may exist for some individuals. For color deficiency, we have different types of individuals that may suffer from different types of color deficiency. We have what are called monochromats, and we also have what are called dichromats. With monochromats, these are individuals who need only one wavelength to match any color, versus a dichromat, and this is a person who needs only two wavelengths to match any color. But yet we also have what are called anomalous trichromats and unilateral dichromats. For anomalous dichromats, these are the ones who need three wavelengths in different proportions than normal trichromats. And last, our unilateral dichromats are trichromatic vision in one eye and dichromatic vision in another eye. So here, definitely indicating for us that there may be some aspects of differences in terms of how people perceive different colors, and may explain why it is that individuals perceive colors differently in different situations. So here, whenever it is that we look at something like the follow, what we call the Ishihara plate test, this is actually used to being able to identify if an individual is color deficient or not. So if you look on the plate on the left-hand side, you'll notice that it has a number of 71, versus the one that's on the right-hand side, the Ishihara plate is actually perceived by a person with a form of red-green color deficiency. So if you suffer from red-green deficiency, you're actually going to be able to perceive what that number may be over there. But a normal person with normal color vision sees on plate number A the number 74 because they have normal color vision in those particular cases. So what color experiences do we have for monochromats? Monochromats have a very rare hereditary condition in which they only have rods and no functioning cones. This is why they have only the ability to see in white, black, and gray tones. So when you look at this issue of rods are not sensitive enough to pick up colors except for these basic colors that we have here. So these are the individuals that suffer from true color blindness. These are not individuals that are very frequent in our population. They are abnormal in terms of their number size, but we do have to understand that people do suffer from being monochromats. So again, they have true color blindness, and they have very poor visual acuity, and they're very sensitive to bright lights in those particular cases because, again, remember, they only have rods and they have no functioning cones. So rods function for low levels of light. They're not sensitive enough for high levels of light. So if you have too much light stimulation, it may potentially be hurtful to that individual in terms of potentially causing pain because the light is too intense for them. All right, that wraps up our discussion associated with color. If you do have any questions for this week in terms of motion perception or color vision, please do let me know. Please feel free to email me or call, and I'll be happy to answer any questions.